Thank you. Okay, so to define continuity, A is a subset of R. It's going to be our domain for our function. Um, and we're going to take a point C in A. Now you might remember from limits that we always took C to be a cluster point. We're not going to do that anymore. Okay, sorry about that. We're not going to do that anymore. We don't insist that our point be a cluster point. So we say that F is continuous at C, and that's the term we're defining. Okay, hopefully this fixes the audio. We say that F is continuous at C if there exists a positive distance delta such that I'm sorry. That's embarrassing. I needed to say that we have an epsilon. Okay, so if for every epsilon there exists a delta such that the distance between f of x and f of c is less than delta for all x in this domain that satisfy x minus c less than. This is really embarrassing, and when I first said that delta, that should have been epsilon. Okay. So now, with this definition, which I hope I have corrected on the fourth try, what are we saying? We've got some domain, but in some sense it matters less than it did with limits because we're not insisting we're at a cluster point.
Excuse me?
Yeah, go ahead.
Can x equal c?
Yeah.
Okay.
Yeah. So again, different from limits, right? So we got some domain and some point. And all we insist is that given you get to pick how close you want the function to be, and then we can guarantee that as long as x is close enough to the point. Okay? Now,
how is this different than the limit? Because this looks just like a limit, like entirely. It just looks like saying the limit is equal to the functional value at that point.
yeah, it's very close to that. Except we have not actually said that we have a limit there. Because we haven't said C is even a cluster point. So it's certainly possible that C is not even a cluster point. Okay. So let's do that as our first. I'm going to call this a stupid example. It's kind of trivial, but let our domain be the natural numbers. If that's a domain, what are our continuous functions?
Well, I would assume ones that map to integers. Because if we map to anything else besides a integer, C wouldn't be a cluster point. Is that right? Or I guess it's, I don't know, I'm just going off intuition.
Yeah. Well, it didn't work this time. So let's look at the. Let's do this definition. Just take A equal the natural numbers. What would it take? Oh, I'm sorry. I really should have said this. A continuous function is, when we say a function is continuous, we mean it's continuous at every point in its domain. Okay, so what would it take to be a continuous function, to be continuous at every natural number, if your domain is only the natural numbers?
I think we have an answer in chat.
Yeah, Madeline. Well, okay, you're right, Madeline. Constant functions would be continuous. But that's not it.
Maybe 1 over n.
Yeah, sure. That's continuous too.
I guess every function could be vacuously continuous. Vacuously true because of the if statement. Because if there's no x that satisfy that condition, then wouldn't it be vacuously true?
So I wouldn't call this vacuously true, but
Okay.
you've got the right answer. Okay. There exists a delta. So if my domain is the natural numbers, I can take delta to be a half. Right? And then the only points that satisfy x minus c is less than a half. Well, the only point that's going to satisfy that is my one natural number, c.
Well, then can't you make every function continuous if you can just pick x? Or you can just pick c? Like in any domain, because you can always get this to be 0.
Mm.
And then this top part would also be 0 all the time. So then wouldn't everything be continuous everywhere?
Okay, so explain it to me one more time, Daniel. What am I going to make 0?
So, it's for all x and c. Okay, never mind.
Okay.
But for all, bumps it out.
Yeah.
Well, if you pick a small delta, so that there's only one x left, which is c,
Yeah.
then it's gonna be continuous, right?
Yeah, as long as you can pick a small enough delta to do that.
I guess since we're on like the real numbers, you can't like pick the smallest. That doesn't really work.
Yeah, that's the whole point. Is it
Okay.
usually we're not able to pick a delta like
Okay.
that. But if our domain is the natural numbers, sure, take delta to be a half, and then you're good.
So if we have any finite finite domain, everything's continuous.
Yeah, and the way we usually state this is a discrete domain, which means a domain where you have no cluster points. So I hope everybody sees why this is true. I was going to write out a little bit of an explanation for why every function from the natural numbers to the reals is continuous. Because we would let epsilon be given and take delta to be 1/2. Let C be a natural number, then the only x in the natural numbers satisfying the distance requirement, so it would satisfy x minus c is less than 1/2, would be C. And obviously, when we look at the distance between f of x, which x would be c, minus f of c, that's 0, which is less than whatever epsilon we were given. Okay. So, quite trivially, if your domain is the natural numbers, your function is continuous. That's not, I wouldn't say that's something to memorize or anything. That's not actually going to be a useful fact. But it's an aspect of the definition to think about. Okay? We can actually go a little bit farther. If the point C is not a cluster point of your domain, then your function is just automatically going to be continuous there. So I'm not going to write this down, but let's think about that. A cluster point is a point that we can get close to, we can approach. So if you're not a cluster point, that means that there is some distance delta, such that there are no other points in the set A that are within distance delta of that point. Okay. So we'll be able to take that distance delta as our delta in the definition of continuity, and we'll trivially get that our function is continuous. So we didn't say that the point C has to be a cluster point, and indeed, if it is not a cluster point, then continuity is trivial. So it's sort of only interesting when it's a cluster point, but there's an important reason that we'll see. It might actually be next semester that we'll see why we want to let functions be continuous at non-cluster points. Okay. Any more questions about this definition? It's the second most important definition we've had so far. The first would be the definition of the limit of a function. No?
Yeah, I have
Oh.
a quick question.
Go ahead.
So,
is the purpose of this second part where we have the delta, is the idea that if the function is not continuous way over yonder, that doesn't matter. We just have to be able to find some, even if it's super 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 small point where the first condition is true. Sorry, that was probably not a clear
No,
question.
that's good. That's good. No, I got it. Yeah. So continuity is saying you're continuous at the point if when you look at x values nearby that point, the function values are close to. Okay. And so what is continuity guaranteeing? It's guaranteeing that you say how close you want the function values to be, and there is some distance where we can say, yeah, if you're that close to the point, your function value is guaranteed to be that close. Okay. So I should have drawn a picture, but I'll draw it now. If that's our point C, then we pick an epsilon, and epsilon is on the y-axis. Those are both epsilons, okay? And then we want there to exist a delta. I'll take my delta to be there, and that was C there. This was f of c, and we want there to exist a delta such that if you're within delta of c, then your function value is within epsilon of f of c. Okay, we're actually not going to prove a theorem today, I don't think. But we'll state a theorem. This is one of those theorems that you probably shouldn't call a theorem. I would be tempted to call it a fact. Okay. Let's say that you've got a function f with domain A. This is continuous at the point C if and only if for every sequence in the domain that converges to that point the sequence of function values converges to f of c. Okay. Think about so this is probably the last time I'm going to mention this. If C is not a cluster point, then the only sequences that converge to C eventually are constant. Okay? So obviously, the sequence of function values is going to converge to f of c. Because eventually the xn's are going to be constant. Okay, but now let's think more broadly. What if C is a cluster point? What if we're in the kind of standard situation where our domain is an interval? Then what does it mean? Okay. Well, any way that you approach that point, the function values have to converge. And in fact, they have to converge to the actual value of the function at that point. Okay? So, assuming that C is a cluster point, for our function to be continuous at C, we need I'm going to break it down. I mean, I could say this as one single condition, which Daniel has essentially already pointed out, but I'm going to break it down into three. We need the function to exist at f of c, because otherwise you have no f of c to put in that definition, so it just can't hold. We need the limit to exist. Again, I'm assuming that C is a cluster point. Remember, what would happen if C wasn't a cluster point? Well, then we wouldn't have a limit there. It's not that the limit would diverge or anything. We're not allowing ourselves to talk about a limit at a non-cluster point. So, okay, and then the final thing, we need those two to be equal. Okay, that's it. At a cluster point, we really are just saying, and you could simplify this to just the final one, because that sort of implies that both of those things exist. The function equals the limit. Okay. So continuity means any way you want to take to get close to the point in the domain, your function values will get close to the function value there. Okay.
Can I ask about the case in which C isn't a cluster point? Just wanted to clarify something like that.
Yeah, of course. Go ahead.
So you said every sequence, that it has to end up just being constant in the table, because otherwise, if C isn't a cluster point, it's something that could be close enough to converge, so it just ends up having to be C itself constant.
Yeah, perfect. Yeah, so if C isn't a cluster point, then really all you need, well, not really, all you need is the function has to exist at that point. And then it's automatically continuous there. Because there's no way to violate the definition, as long as the function exists at that point.
Excuse me, so, this is kind of messing with my intuitive understanding of continuity. So if I gave you a function that maps the rational numbers to themselves, just like the identity function, that would be continuous everywhere, because we can talk about its limit at every point.
Yeah,
Okay,
you know, hey, let's do it. Let's do it. Let's write out the details, right? So we'll see why that satisfies the definition. Okay. F maps the rationals. Um, I mean, I'll take the codomain to be the reals, but by f of a rational number is itself. Okay. This is continuous at every point. And I see why it's messing with your intuition. Because, right, I mean, it's not even defined. But, I mean, like, any point we pick, there's all these values, you know, arbitrarily close to it where it's not even defined. But we only care about the domain. Right? We only care about this set A. Okay. So how do we prove this? Let epsilon greater than 0 be given. And set. What delta should we use?
Shouldn't we set 1 over delta to be less than epsilon? Or no, that's what the sequence is. Something like that.
Delta equal epsilon.
Yeah, so delta equal to epsilon.
Alright, delta's a real number too.
Yeah. Then, for every point C in the domain, and every point X in the domain with, what do we need to satisfy? We need X to be within delta of C. We have f of X minus f of C is less than epsilon. And the reason for that is that f of X is just X, f of C is just C, and epsilon was just delta, or I guess it would be better to say that delta was just epsilon. Yeah? So yeah, the identity function on the rationals, totally continuous. Okay? Just like any function with the domain, the natural numbers, continuous. Okay? Any isolated point in your domain, so isolated point essentially means not a cluster point, your function is guaranteed to be continuous there, as long as it's defined there. But you know, when we say that a point is in the domain, we kind of assume that it's defined there. So you're totally you're guaranteed to be continuous at any isolated point. So you can say the definition is only interesting at cluster points, but you know, but again, like I said, next semester we'll see why we stress so strongly that continuity has to include the non-cluster points where it's trivial, but there's a really good reason for it.
Professor,
Yeah.
could you give an example of a function that is not continuous?
Yeah, easily. Example. Well, let me just. I can just take a removable singularity and then change my function value there. So f of X equals 1 if X is not 0, and 0 if X is 0. This is not continuous at 0. And again, in the definition, that would be our value of c. Why is it not continuous at 0? Well, you would set... So now we're trying to negate the definition, so we get to pick the epsilon. Right? Set epsilon equal to 1/2 for every delta. Every positive delta. What point should I look at? I want to say that f of some point minus f of 0 is equal to 1, which is greater than epsilon. That's the punchline. But what point should I evaluate my function at?
0?
I don't want to evaluate at 0 because then I'll actually get 0 there, and I want 1 there.
Oh, then I guess it would be at every other point.
Sorry. But I want the point to be within delta of 0.
Okay.
So what's a point within distance delta of 0 that's not 0 itself?
One-third. It's within 1/2 of 0, and it's defined in all reals, correct?
We have an answer in the chat.
Yes, Madeline, of course. And thank you, Daniel, for pointing that out. I always forget to look there. Remember, our favorite constants are 1 and 1/2. So we'll take our second favorite constant and we'll multiply it by delta. Delta over 2. Delta. Delta over 2 is a number that is within delta of the origin, but it's not the origin. Okay? I guess we might want to add in this proof, but that. Okay? So we violated our function distance condition, even though we satisfied our domain distance condition. Okay? Good.
So this is it violating the limit part of the definition. Or I guess if we take, because we have these are all cluster points, those 3 conditions we have, we're violating the limit 1.
Mm-hmm.
Okay.
Yeah, we're finding a point arbitrarily close, whose function value is not right. Not right.
So if there's a hole in the function, it's automatically not continuous because the function value doesn't exist there?
Yeah, you cannot be continuous where you don't exist.
Okay.
So even a removable singularity, so, you know. We did one on the quiz, but I can't remember what it was. But, you know, I'll just write, I'll factor it so it's especially stupid. I think this might have been the one on the quiz. Right, this is not continuous at x equals 1. Because it's not defined there.
Professor, can I ask a question about the previous example?
Yeah, of course.
So, the reason that delta, if we just said, if we just said 1/3 instead of delta over 2, the issue that 1/3 minus 0 is not, the absolute value of 1/3 minus 0 is not necessarily less than delta.
Yeah, perfect. Yeah. Yes, that's why we can't do 1/3. We need to find a point that's arbitrarily close to 0. And the measure of arbitrarily close is the delta. Yeah. Okay. Oh. Now, let's do a few more examples while we're here. Let's go back up to assuming that it's a cluster point. What do we need? We need the function to exist, the limit to exist, and those two to be equal, right? So that we're going to do some examples where we actually have already proved all this stuff. Okay. Function exists, limit equals the function. Okay. F of x equals x on the domain. Let's take our domain to be the whole real numbers. That's continuous everywhere. It's not like it would be hard to write down a proof of that, but we've already got a proof of that, and that's the fact that we've computed that limit at any point c, and we found the limit at any point c is equal to c. I saw a great Twitter yesterday that I can't resist sharing. The guy said, "Here you go. Here's a useful approximation for pi." I don't know. You cracked me out. But anyway, that function is continuous everywhere. We also proved that x squared is continuous everywhere. Because we proved that its limit as you approach c is c squared. What are the limits did we do? We did 1 over x as long as x is positive, right? So what would be our domain there? It would be the open interval from 0 to infinity. Why is that function not continuous at 0 even if I included 0 in the domain?
The function isn't defined as 0, so you can find a sequence that converges to f of 0. It just doesn't exist, right?
Yeah, perfect. The function is not defined at 0, so it cannot be continuous at 0. Why don't I just define it to be something at 0? Why don't I just go ahead and say, I'll make it 1 at 0. Does that fix it?
It's defined but not continuous.
Mm-hmm. Why? Why isn't it continuous?
Well, I feel like couldn't you do the same trick where you put like you divide delta by some, probably delta over 2, and then you always have a distance. I'm not sure. Well, I feel like there exists some delta such that for every epsilon I can't really produce it at the top of my head right now.
Mm-hmm. You're right. We could definitely do the definition, but there's an easier way.
I think I know.
Go ahead.
So x equals 0 is a cluster point, so we can apply that thing from earlier where we said that for a function from A to the real steady continuous at C, we need the function to exist, and we need the limit to exist.
Mm-hmm.
But we need the function to equal the limit. So here the function is going off to infinity as it approaches 0, but then it equals 1.
Mm-hmm.
Kind of.
Mm-hmm. But the reason I point this out, it's actually the second of those conditions that we violate.
Madeline has the answer in the chat.
Yeah. Oh, yeah. She does. There is no limit at 0. Right. Infinity is not an acceptable limit to us. That limits can't be infinity. Now, if we were, there's a way to do it. You in other advanced calculus courses, you might consider a limit to be that's infinite to be a limit, but here we're definitely not, and everything works out. So if we don't have a limit at 0, okay. I mean, we also violate the third condition. Obviously, our limit is not equal to our function value. Okay, but before that, we just don't have a limit. Okay. So this red one, this is not continuous. And x equals 0. You can only make a function continuous. Here we try to make a function continuous by defining it at a point. You can only do that if you think about it. You can only pull that trick off if it's a removable singularity. By which I mean it's sort of the definition of removable singularity. But I mean, if the limit at that point exists, and then we go set the function equal to that limit, then we've made it continuous there. Otherwise, no matter what we set the function equal to, it's not going to help make us continuous there. Right? We would have to have the limit exist anyway. Okay, so let's look at one final example. This is Dirichlet's function. Where did I write that? This is an incredibly famous function. 1 on rationals and 0 on irrationals. Let's start by graphing this function. What would that look like?
A bunch of needles just poking up.
I wouldn't say needles. I would say it looks like dots, right? I mean, the dots.
Oh yeah, I'm thinking about just connecting them. I just can't do that.
And there's so many, you might as well just draw a line, right? But then there's so many, there's even more irrationals. So, I don't know, you draw a thicker line on 0. So you got a function. It passes the vertical line test. It really is a function. But that's what its graph looks like, right? It's discontinuous everywhere. But which it's not continuous at any point. Why is that?
Well, because if you pick any epsilon and any delta, you can find either a rational or an irrational number between delta and your point C because of the density.
Yeah. Yeah, exactly. And that's the perfect word, dense. Okay, the rationals are dense, the irrationals are dense. So no matter how close we want to be to our point C, we can find both a rational and an irrational within delta of our point C. So, we can't satisfy the definition. Okay. There's a way to change this. If we change that 1 to an x, then we actually will be continuous at 0. Right? We won't be continuous anywhere else, but we will be continuous at 0. Okay? Okay, so let me end with this final thing. Not related to this section, except related to Dirichlet's function. What do you think the integral from 0 to 1 of that function should be?
Zero. That's my guess.
Why?
Because there's so many zeros to add up that it cancels out all the ones. I don't know. That's what my intuition says.
So nothing gets canceled because there's no negatives involved.
Right.
There's no negatives involved.
There's so many zeros that it just, I don't know, gets rid of all the ones, if that makes any sense.
Yeah, so I would say... Oh, go ahead.
I'm sorry, no, I interrupted, sorry, I didn't know how to speak, but I think it has to do with the fact that, the rationals are countable, so they're just little points, whereas the irrational are, they're uncountable.
Yeah, so that's the way I would put it. Not that there are so many zeros, but there are so few ones. When you're doing that integral, there are just so few ones, because the ones are only at the rationals. And there just aren't that many rationals.
I guess you kind of have to, even though there is some substance there, just by the way how we set some definitions up, it kind of forces it to be 0.
Mm-hmm.
Like by weighting more zeros in there, or just because there's not enough, we get some number that's less than any real number, right? And then if it's less than any real number, but greater than 0, it is 0.
Yeah, that's how the proof would work. Yeah. So I guess I'll end the lecture for this week with, sadly, we're not going to get to this point in this course. We're never going to be able to integrate this function because we're going to learn Riemann integration. And in Riemann integration, this function is not integrable. We don't get to integrate it. If you really want to integrate this function, you have to use a concept called Lebesgue integration. And if you want to learn Lebesgue integration, you have to take the 6,000 level analysis course. But this is the classic example of why you would want a different version of integration than the one we're going to learn. Okay? But again, we're just going to learn Riemann integration. Okay, well that is it. As you can see, all we did was the definition of continuity. We looked at a bunch of examples. It's really important to think through the examples, know how to prove that things are continuous, know how to prove that they're not continuous. And then on Monday, we're going to, what are we going to do on Monday? On Monday we're going to do the boring theorems about how we can add and multiply and divide continuous functions and all that. Okay?
Professor, I just want to say thank you for all of the examples because they were very helpful for me.
Great. There's a few more in the book. Sine of 1 over x is a nice example to look at, to work through. And that's the last one. Oh, Raphael asked, is Lebesgue integration not taught in 4227? And don't quote me on this, but I don't think so. I don't think it's taught in the I think 4227 I think is the 4000, 5000 analysis course. I don't think it's taught there. I think you have to take the legit 6000 analysis course to get it. But I could be wrong. Okay, so I'm going to stop the recording.